Hello everyone. Great that you're joining us today for the public paper reading group of Merantix Momentum. I hope that the people online can hear us. If not, please give us a sign of life. But on the other, if everything's fine, I will briefly introduce the event. So once a month, we have this public paper reading group that is organized by us, Merantix Momentum, and we discuss some of the latest developments in machine learning and try to also bring the community a little bit together and provide a space for you to mingle and speak to each other. So that's also greatly encouraged. Today we will have the event on the European Computer Vision Conference. European Conference on Computer Vision, actually, to which 5 of our engineers and researchers traveled last week. And yeah, it's like one of the finest places to publish for computer vision work. And we're really happy to have 3 of our engineers today with us to bring some of the papers to you and to present some of the exciting work that was presented at the ECCV. One note about the event, this meeting will be recorded and will be later uploaded to our YouTube channel. If anyone's not fine with that, please either say something now or we can for sure figure it out somehow. Cool. I think then we can get started, and I look forward to handing over to Vinny or to Thomas. Okay, perfect. Then take it away. Okay, yeah, the music is turned off now.
Perfect. Yeah, nice to see so many faces here, also a few familiar ones. So unfortunately, Max and Adrian, who also joined our trip to ECCV this year, couldn't join. But we have Vinny and Miha here, and maybe to explain why we went to ECCV at Momentum, we have a kind of a company perk. So every employee can go once a year to a conference of their choice. And all of these people work in the computer vision space. So the ECCV was like a natural choice. Yeah, we just came back 1 week ago. And to give you a feeling how it was, this was basically the conference party. Was one of the finest conference parties we ever went. It was really a blast. We met a lot of cool people there, had nice discussions, and yeah, a few drinks, of course. And the whole conference was in Tel Aviv, also a very nice location. And Tel Aviv is like another capital for startups in the world. So you feel like a startup vibe there. Also at the conference, a lot of startups were present. And here you see some representative photos of our trip there. So we got a little bit of sunlight in the last weeks of the year. And we also collected a few outstanding papers where we thought this could be interesting to you, some unusual ones. And Vinny will start with his pick.
Thank you, Thomas. I will present 2 papers today. It's a bit hard to come up with the most favorite papers that you like the best. But yeah, I just picked this because also I was at NeurIPS 2020 virtually, and I met these guys at their booth, and they presented a paper about neural image compression. And I found it very interesting because, as it seems, these neural compression methods are better than anything what we have so far, like better than PNG and whatsoever, and JPEG. And the problem is kind of that it's very expensive to do this compression. Requires a lot of compute. And the big question back then was, can you do it also with video? And now they did it. So I found this quite interesting. So they actually came up with a neural compression algorithm for video. And I'm just going to walk you through this real quick. So just to begin with, how does such a neural image compression algorithm work in very general terms? So what you want to do is you train basically an autoencoder network. You get an image in and an image out, and then you apply some kind of control term on the latent code to make it compressible to a small number of bits. And these bits you can also then like store in a file or transfer over some, bandwidth limited connection. And how do you train this autoencoder? So there's basically a loss that consists of several terms. On the image on the left shows the input, and then there's basically a term which is R that controls the rate, like how many bits you have in your latent space of the autoencoder. And there's another term which is this D, which stands for reconstruction or distortion. So basically it's an MSE loss that encourages the model to reproduce the same result that you put into the autoencoder. And there's this trade-off between rate and distortion, which can be controlled with the lambda parameter. So you can optimize for higher compression or for better reconstruction as you want. But one problem with this naive approach kind of is that if you think about the mean squared error, it quadratically penalizes deviations from the original image. And what happens is once you compress, once you lose information, your result gets very blurry because that's the optimum of this squared error. So basically, the model tries to get as close as possible to this source image, but where it loses information, the picture becomes very blurry, and that's actually not what you want. So what these people did is they apply a third loss term, which is driven by a GAN discriminator, and it encourages the model to produce realistically looking images. And what actually happens is that because of the third loss term, the overall at the MSE, the reconstruction loss, it's worse. When you add this third loss term, so the reconstructions are actually more off, but they look more realistically. So that's something that we as humans like. We don't care so much if the grass looks exactly the same like in the input, but we see that it's grass and it looks good, it looks sharp. And that's why when they do a user study, they usually get much better results using this method, even though if you compare the MSE loss, the results are worse. So how do we apply this to video now? This was the big question, and the way they did this was that they copied over some ideas from classical video compression algorithms. So basically what you do in video compression, because the frames are highly correlated, you don't transfer each frame one by one, but you have a distinction between P frames and I frames, where P frame means that it's a predicted frame and it's predicted from the previous frames. But as you can imagine, if you always condition on the last frame and you do this for many steps, the error accumulates. So at some point, you need to transfer a frame in full resolution, and that's what's called an I-frame. So basically, I think in the paper they do this every 60 steps. They do this. This part is just a usual neural image compression algorithm. You have the GAN discriminator here, and you have basically the latent which is transferred. And then for the P frames, for the predicted frames, there are basically two parts that have to be transferred. One part is the flow, which is basically estimated from two consecutive frames. And the second part is residual. So basically the flow tells us how the pixels are shifted from the previous frame to the next one. And our residual tells us what is the little error that comes maybe from objects that are newly introduced in the new frame that haven't been there before, right? And how this works is you do this flow prediction. Then you do the warping, like with the flow, you can basically warp the pixels from the previous image. All this information is passed to an encoder, and then you get a latent code again. And afterwards, like on the other side, basically on the decoder side, this information is decoded, and you get the flow out, which you can use to warp the image, which you already have from the previous step. And there's another step in this, at this point, where the model basically predicts how, like the areas where it expects new information to be introduced, and these areas will be blurred. So if a new object appears suddenly in our video stream, this part of the model will basically blur it out to make it easier to add the residual on top, and that's what happens in the last branch. So you basically have another set of, basically another autoencoder that encodes the residual, and basically the residual is added on top of this warped image at the last step, and that's it. And it's very nice, it works. They conduct a user study where they basically compare different algorithms. All of these algorithms are basically set to the same compression level. So they are allowed to use the same space for the latent codes. And if you ask the users then which video they would prefer, like which they find more close to the original video, most of the users agree, like in all of these comparisons, that the neural codec is better. And also when you compare it to H.264 or to this one, which is the standard codec, which is often used right now, you find that the neural codec is much better. The only problem, as I already said at the very beginning, is hardware constraints. So this processing, like because you have all these different neural networks and they take a long time to execute, it's very expensive and it doesn't run on a normal phone or on commodity hardware. So it's maybe a little bit into the future, maybe a few years into the future until this will become reality. But it's to be expected that at some point neural codecs will replace what we have, and that's actually quite fascinating in my opinion. And yeah, please.
Just a comment on that. So in the phone there is a special chip for making the H.264. So it's not fair to compare it to something that is not running on it.
So maybe repeat your question for the audience, for the online crowd.
Just a comment in the phones, for example, or even a computers, you have a special chip that is doing the compression already. So,
yes,
then if you compare it to a CPU implementation or even an AI implementation with a small network, it's totally fair. You have to wait for the AI accelerators to.
Of course, run. Yeah. Yeah, that was also like one point that they discussed at the poster. Yeah, like which AI accelerators will be there in the future, and basically, you know, like how to tailor these models to accompany for these hardware changes. That's a very good point.
One question that comes to my mind is whether things like domain shift are a problem for these neural compression methods, because for H.264, I would never worry about it not working on some kind of video that was never trained during the training. That didn't happen. But for trained methods, I'm not sure if I shouldn't worry about those things.
Yeah, I think that's also a very good question. I'm obviously not like very deep into this topic. I just had a brief discussion with the guys at the poster. So what I would think is that because they trained this on natural images, that this model is kind of like the distribution it's trained on as natural images. So I guess it works well for this. If you have something like synthetic data, I would also suspect that it doesn't work as well.
Maybe one related point also to what Fabian said there. It's also interesting to think about that the autoencoders are actually used also as an auto distribution detection model. So basically, if you don't train them on a certain distribution of data, they can be used to detect that the data doesn't come from that distribution. So that I also see that being a problem maybe for the neural compression. Yeah.
Okay, great. Any more questions, remarks from anyone? I think it makes sense to stop for a while, like after each paper, and just like get a little bit into the discussion. And once you guys are happy, okay, there's one more.
What is new here? I mean, this type of stuff, a lot of people have been working on it. I know that Qualcomm has been doing research in this field and also using GANs. So what exactly is novel here?
So the question was, what is new about this algorithm in comparison to what has been there before? I think it's, at least in my understanding, the first neural video codec that is out there, like one with which is working only with neural networks, and it has only like very very limited amount of classical components in here. So I think if you look at the architecture diagram of H264, it's actually quite a lot more complicated than this. So this is in comparison to the previous codecs, like the one that are hand engineered. I think that's quite a bit of a simplification. And I think there's also like a follow-up work which does this with transformers, or that they said that they were working on this at least, and it will have even a simpler architecture. So I think like what I find fascinating about this is that you can, like, there are basically books about H264, right? Like there's so much to know about this algorithm, and you can do it with neural networks, and you get better results. Like actually, like judging from at least from a human perspective with a very simple approach. That's what I find fascinating and new.
Questions regarding. So you said I think that they have about 50 iframes after each p frame. I was wondering, I think a good number for this, I would suspect, depend very much on the content of the video. So if you have a picture where a few things changing, probably you would use a larger number. And if you have cut in the video or something like that, it probably doesn't make sense to use a completely new images like that. So
Yes, that's true. They did, as far as I know, they didn't consider this so far. But yeah, it's an obvious limitation, because like if you have a hard cut in the video, like a new scene appears, then this model would fail at this point, because they are not able to adaptively adjust like the number of p frames. That's a good point.
Okay.
Everyone, please hold the mic very close so the loudspeaker picks up on it.
So, okay. Faces would be a good test in figure, because humans are so good at it. So, but there's another question I have. Did they actually use the super frame rate kind of an expansion for that? Because you can actually do it. You could actually increase and put in between frames to the frame rates.
That's a good question. I don't know, to be honest. I would have to check the paper. All right. If there are no more questions, I would move on to the second paper. Yeah, it's actually work that I did a year back for my master thesis. So what this is about is it's about neural image stylization. So what you want to do is stylize an image, and I think maybe all of you or the most of you are familiar with neural style transfer and these algorithms. So it's quite cool what you can do with these. If you look on the right side, I was told to use the mouse as a pointer, so I will do this now. If you look here, you can see that you get quite impressive results. You can define arbitrary style images and content images, and you get nice results out. But the problem with many of these approaches is that they are not very adaptable by the user. So what you can do is you can change the style image, but that's about it. And you have to live with the result. But maybe it would be nice to define which elements or which like parts of the style to transfer. So in some regions, you might want to transfer the color. In another region, you might want to transfer only the texture of the style, and so on. And you might want to be able to adaptively control this for the image. And that's basically what this is about. And what we looked at was algorithmic effects, which have been there for quite a while, like classical computer vision effects, where you have something like edge enhancement filters or bilateral filters, and where you have adjustable thresholds in these filters that you can control, and you know exactly what these parameters are doing in those classical filters, and you know how to adjust them to get the results that you want. So, for example, for the image on the left, you could imagine that you select the regions where you have contours, and you like, for example, the region where the background intersects with the shirt, and you increase the contours there, and then you get these black lines that you see. And for other parts of the image, you might want to have less contours. And what we did is basically we tried to combine these two approaches, like interpretable and controllable computer vision filters and example-based machine learning methods, and try to kind of come up with a solution that's combines the best of both worlds. And how this works is we basically re-implemented these computer vision filters in PyTorch, made them differentiable, and then we have 3 steps in this architecture. So at first we have basically the classical style transfer algorithm that executes the style transfer and generates some result. And in the next step, we would try to take this result and transfer it to the local parameters of our differentiable filters, which are here. Once these parameters are updated, what it means is basically that our differentiable effect is able to reproduce the result from style transfer by setting the right parameters. And once we have those parameters, we can, in the third step, which is the bottom row, give those to the user for readjustment. And I will show you a video, like, quickly how this works in practice. So you start with a style transfer algorithm. You can see, like, in several steps how the style is transferred to the image. And once it is finished, you can basically developed an app where you can select parts of the image, and then you have basically a bunch of sliders which are not visible in this video, but they are in the app. And then with these sliders, you can go ahead and you can say, I want a little bit of contour here, I want a little bit less color there, and so on. And then you can actually control what the style transfer does by adjusting these sliders. Yeah, so far about that. Any questions?
Does the app on the fly learn from? So you can give me an example image. Does the app on the fly learn based on the whole thing, or?
So if I understood the question correctly, was if it learns on the fly. So if you can put arbitrary images in there and it works. So, so the classical style transfer, how it works, it's an optimization algorithm. So you don't have a trained model. You basically do gradient descent for several steps, and with these gradients, you update your content image until it matches the style of the style image, and that's obviously quite expensive procedure. So it takes a couple of minutes on a GPU, worst case. But yeah, we can do this with the app if you have a GPU and if you're willing to wait. Another alternative would be to kind of train a neural network that can do this operation for you. But we at least for this paper, we didn't get to doing this for the algorithmic effects. So that's kind of future work to make it quick. Was that clear? All right. I think if there are no more questions, I would happily hand it over to Miha. Thank you, Vinny. Thank you.
Yeah, hello everyone also from my side. So yeah, as Vinny already said, my name is Miha. I am a machine learning engineer at Merantix Momentum. And yeah, today I will talk a bit about adaptive token sampling for efficient vision transformers. So in general, there was quite a bit of transformer papers in the ECCV. So apparently they're really taking over computer vision world a lot. And yeah, even though I wasn't so familiar with transformer before, I think this paper is really nice, and hopefully I can also make it sound interesting for you. Yeah, paper is written by the following authors here from Microsoft, UC Davis, Technische Universität Berlin, University of Bonn, and so on. So where the authors kind of come from is they argue that like in kind of conventional neural networks, the amount of computation that is used is basically proportional to the size. So let's say to the image dimensions that are being input into the network, and that actually instead complexity of the content of the data process should be used. And further, they argue that typical input data for neural architectures has like an inherent complexity that is actually independent of the input size. And finally, they claim that static token resolution in vision transformers leads to having unnecessary computational overhead. So yeah, in more plain, simple English terms, we can observe the samples here on the left side of the slide. So for example, in the top row, we see like an image where like there's not a lot of going on. There's a lot of like kind of correlated pixels or correlated tokens if we want to use the transformer language. And in that sense, they argue that for prediction on this kind of input image, a lot of less tokens should be used to reduce the computational overhead. And yeah, on the other hand, like in the bottom row, for example, we have kind of a lot more detailed image. And yeah, they argue that for this sort of image, like more tokens are needed to make a successful prediction. Yeah, and how they do that is they introduce this adaptive token sampling module, which essentially at each transformer block stage takes a set of input tokens I. And of course, since we're doing classification, also we use this trick of concatenating there also a classification token, which is in the end used to be input into the classification head and makes the final prediction. So how they basically assign the scores for each token is that they compute this scores as attention of this classification token towards each of the input token, which we can see yeah here in the top row of the matrix. And well, not only do they use the attention value of classification towards this input token, but they also multiply that with the norm of each token. So kind of intuitively, if they argue that if the value of the token is very small, then also probably it's not very important for the task anyway. So now that they compute this scores at each of the stage, they basically kind of interpret these scores as probabilities. And yeah, what then they can do is they can create like this distribution of the scores. And then they essentially sample k number of tokens, where k is kind of like, let's say, a hyperparameter that we define in the beginning. And like one interesting thing is that they don't, they basically sample with repetition. So what it implies is that then each of the tokens can be sampled multiple times. So if we have, for example, one token with a very high score, it could be that even though we sample k times, we sample always the same token, and then essentially we end up with only a single token. And that's how kind of this adaptive mechanism here works. Yeah, so finally, they also reduce in the end the attention matrix by using only the rows that are associated with the tokens that were sampled from the distribution. Yeah, here we can also see how the number of tokens gets reduced throughout different stages. So at each stage we make the sampling, and then effectively we reduce the number of tokens at each stage. So what like this is all about? Actually, it's in the end, as I said already in the beginning, it's about reducing the computation cost. And like what they claim by doing the experiments on ImageNet classification is that they can retain essentially the accuracy on ImageNet, and they reduce the number of flops by around, let's say, 30%, more or less. I thought I had one more slide with some ablation studies, but apparently it's not here. Yeah, so maybe there are some questions about the method.
So it's still so that all the tokens have the same size.
Yes, all the tokens have the same size.
Okay, so they are not actually making small tokens. Because that would actually kill the transformer as well.
Yeah. So yeah, in general, the transformers have the issue that
the
computational So in general, as far as I understand, the computational complexity comes from the increased number of tokens that we have, because the attention matrix then gets bigger by square, right?
So then you say that you need smaller number of words in order to describe images.
Really?
You need smaller number of words to describe images.
Yes, smaller number of tokens, yes. All right, so yeah, if there is no more questions, I will hand it over to Thomas.
Thank you, Miha.
So let me go next. Does that work?
I'll give you this one.
Let's try again. Now it works. So if you think of what was the hype topic of this ECCV, it was nerves. So there were like lots and lots and lots of papers about nerves all over the place. And also a few interesting ones. And we picked like one in particular, which we found interesting, which is post-nerve. So modeling human post-manifolds with neural distance fields. And this is a more unusual application of nerves. So maybe to give you a short rundown on nerves. So a nerve is basically a neural network which learns an implicit representation of your input. This could be, for example, a 3D volume, some, for example, map that you just observe sparsely and so on. So for all kinds of inverse problems, you can apply these nerves to reconstruct them. And here in this paper, they proposed that they could learn the manifold of possible poses of humans and use this for interesting applications. So looking at it from a bird's eye view, you have these realistic poses here, and these are the green squares, basically. And then there are unrealistic poses, which are basically these red circles here. And the red circles should be basically outside of the manifold, and the green ones are on the manifold, basically. And now they train this post-nerve to represent it so that the level set of the representation of the nerve is basically covering the manifold of your data. And now you can do fun stuff with it. So you start with some pose. Let's, for example, here look at these weird poses here. And since this is basically more like a landscape and you have a differentiable model, you can do optimization on it. So you can move towards your manifolds that you learned and create out of a unrealistic pose a realistic pose. And you can use this now as a prior in other models. So they did a lot of different experiments on how to use this. So you can use this for detection. You can so like for pose detection, for pose denoising, and tracking of humans, and much more. So they have like very vast experiments in that paper. But now I just want to like cover the concept. So you have here this observation on the left, super noisy. They basically use these observations, do this optimization to move towards the manifold that they learned. And then they get this denoised basically motion out. And it's very close to the ground truth and not noisy anymore. And they, as I said, did this in lots of applications. And in the end, the idea is relatively simple. So what they do is they have a set of realistic poses, which are described by key points. And they feed these set of key points as a vector into their nerve architecture. And now the output should be 0 if it's like a true pose. And it should be greater than 0 if it's not a true pose. So they apply this loss function on it to train it. So first of all, they have the set of all the poses in their data set. And you may be wondering, yeah, I just have like realistic or like real poses. Where do the non-real poses come from? They basically do something similar like you do in for example, stable diffusion, like in these diffusion models. You just add noise in one way, and now you basically try to find a model to do the opposite. So they have their poses. They have basically a noisy version of the pose. And now they can calculate the distance of this noisy pose and the real, basically the real pose. And these they put here into this distance. They put here into this left loss function as this d, and then they also put the noisy pose into the nerve, and then they observe some output, and then should be the same as the distance that you basically calculated before. And you do this also like with the real poses, but there the distance, of course, is 0. This is one loss. And then they have this iconal regularization term on the right, which basically takes like the absolute of the gradient of all the noisy poses, so the non-realistic poses, -1, so that the overall pose has like a unit norm gradient, so that basically the landscape that you're learning has a nice shape. And this is basically it. That's how you learn this nerve, and you can use it for various things where you basically want to do this denoising operation. So in the end, you take your distance of your, you basically take your pose on the manifold, push it through a network, you get the distance out, and now you're minimizing this function like with gradient descent and get the realistic pose and use that for various applications, which is super simple and very nice. Are there any questions?
Very good. Sorry.
Sorry, I'm a little confused by the use of the term nerve here. This is where is the radiance field here? The NDF is basically a distance field, and neural distance fields have been done much earlier than radiance fields, I think. So I don't quite understand where the radiance fields come in here.
So you're referring to the radiance fields encoding that you do like in classical nerves. So
yeah, I mean, you're learning a distance function is a different to learning a radiance field.
Good point. I think it's just good to be on the hype train, and everybody's talking about nerves. Are there more questions?
Coming.
What is delta F of data again? You kind of lost me over there.
Which one?
The sigma on the right. Do you have delta F of you see what I'm saying? What is the function of UDF for?
So you basically take here the absolute derivative and -1, so that in the end you want to optimize so that these samples here, which are the noisy ones, have unit norm. So this is the gradient. And with the whole term, you basically constrain it that it has a unit norm. Otherwise, the values could, for example, explode, and you don't want to have that. You want to have like a nice functions to later do gradient descent. Going back, like the thing that you want to learn should look like this and not have like crazy spikes and everything in this red area. There are no more questions. Or did this answer your question, first of all? Yeah, just do that. I think this is the easiest. So let me jump to the next paper. So transformers again, but now the same but different. So they call it Relationformer. A unified framework for image to graph generation, and the title says it all. So in many or in some vision tasks, your final output should be a graph. So here you can see some examples. You input, for example, this satellite image, and you want to have segmentations of roads, of rivers, whatever, and want to analyze the graph that comes out of it. Another example is here you have these vessels, very common if you want to design a new surgery method, that you first go for like real vessel data basically, and analyze the graph structure of how you, for example, have to navigate where could be issues in the blood flow, and for that you need like the graph of the vessel system. Or on the right, you want to do like a semantic scene analysis, and for that you need to know all the objects in the scene, but also how they relate to each other. So in the end, the thing that you want to operate on is a graph. And the authors of this paper, they asked themselves, why not directly predict this graph out of the image? Why do something intermediate like segmenting, then predicting the graph or something like that? So they came up with an architecture to do that, and it's based on transformers. So let me guide you through it. So you have your input image and you put it through a pre-trained CNN backbone. Then you basically get all these features and you slice them into different tokens, same as like classical vision transformers, and encode them with a vision transformer encoder. And now you have a decoder where you have object tokens, and these object tokens are basically anchors, so reference points on your image that you input into this decoder, plus this RLN token, which has like a special function in this architecture, and they figured out that it has an essential role. So these object tokens now use like the attention to the data from the encoder to produce features for each of these objects. In addition, you have this RLN token, which collects global information about the scene, which is then encoded in this red feature. Now you can use classical object regression heads on top of the object tokens, which you can see here, where you have like a class prediction of is there an object or not, and then also the basically bounding box of that object, like you would do like in a faster RCNN, similar fashion. And this is the upper branch. And in addition, now you have an object detector more or less. You also have a branch for predicting the relations. And what they input into this model is basically each combination of these object features plus this scene descriptor in the middle. And first they tried out, for example, inputting all combinations, or like here predicting all combinations. So this would be a lot of tokens, which explodes very quickly with a number of objects. But since they now can combine post-hoc all the different objects in this module, the computation is relatively reasonable. And yeah, again, for them, adding this extra global token was essential. And now, after the predicting these relations, they can construct the graph using these predictions and the basically class probabilities. And that's basically the method. They trained it and had like very good results on several benchmarks. Are there any questions relating this paper?
Maybe.
So what training data do you need for that? Just the graphs or also the object detection data?
You need all of it. You need the images, and for labels, you need the graph and also the bounding boxes. So here you can see the bounding boxes, but you also need the graph.
And in the segmentation example, what would be the bounding boxes?
That's a very good question. So I think here they detected key points, but I'm not sure. We have to read it up.
Could you repeat that part, how the complexity is reduced by that global token? Because I got the part where the complexity grows quadratically with the number of objects. And then we do something with the global token that makes it not quadratic, but I didn't get that part because we don't do all with all anymore.
So in the decoder, you could predict all relations directly, and this would explode pretty quickly. So instead, they just predict basically these object features. And now they combine these object features in this branch to predict the relations. And what they figured out is if you do this without this global token, it doesn't work. You have to add it.
Okay, so the complexity is reduced by doing it not in the decoder part, but separate from that. But to make that work, for that, you need the global token.
Yes, exactly.
Okay. So that relation prediction is still quadratic with the number of objects.
Yes.
Okay, cool, thanks.
I'm wondering if they comment, why do they need to use a CNN backbone? If it's necessary, or you could just use like a normal transformer, missing transformer.
So I talked with the guy at the poster. I haven't read actually this part of the paper, to be honest. And he said something like, yeah, we try to save compute. But maybe it's also like stated in the paper, but I don't know.
Can we discuss a bit how the inference is happening? So like I got it, so we have image, let's say, during the prediction, yeah, and we don't have any extra knowledge than input. Then we fitted it and we fit it to the encoder. Then it looks like we have the RLN token, some default one, or how does it really happen?
So let me guide you through the inference. So you have your image, you push it through the backbone, through the encoder, and now you have like your classical BIT features. Now you have these object tokens, and these are basically anchors. So you distribute reference points over your image, which are your anchors, and then you feed them into the decoder. And for each anchor, you get basically a prediction. Now you have these predicted class and bounding boxes, and you do like classical non-maximum suppression, and then sort out all the low probability objects to get the objects that are detected. And finally, you now take the related tokens from the decoder, push it through this relation prediction to get the links between the objects that you have detected. Now you have the relations and you have everything to construct the graph in the end.
Object tokens are learned like in vector, I assume. Like these are learned, right?
Yes, so they use the same thing as in Dettor. So this was it from our side. So also happy to take questions offline and discuss the papers. And there were many more which we can share, but these were our highlights. Yeah, and thanks everyone for joining today.